Good morning, guys. Today we're going to start the online section of the fluid mechanics. Okay. So we start from chapter 5, conservation of mass. Okay. So before we talk about the conservation law, I think the first lesson is to introduce the flow rates. You need to know how to calculate the flow rate before you can, calculate the conservation of mass. Okay, flow rate. There are two types of flow rate we commonly use. One is called volumetric flow rate, Q. We use letter Q by convention. It means volume per time, right? So how much volume of fluid being passed per unit time, okay? So obviously in the SI unit we use cubic meter per second. In English unit we use cubic feet per second. Okay, so this is volumetric flow rate. So volume per time. Okay, the other flow rate often used is called mass flow rate. We use m dot to represent the mass flow rate. So it's mass of the fluid per time. Okay, so the unit could be, in SI unit is kilogram per second. So there's these are the two commonly used flow rates. Okay, so the conversions between Q and m dot. M dot equals rho, the density, times Q. Very easy. Okay, simple conversion. So if you are given a volumetric flow rate, you can easily convert into mass flow rate by multiply a density. Vice versa, if you are given a mass flow rate, then you divide it by density, it will become volumetric flow rate. Okay, it's very easy to convert between the two flow rates. Now let's look at the conversion between velocity and the flow rates. So you don't go from velocity to mass flow rate directly. You convert velocity into volumetric flow rate first. Okay. Then after you get the volumetric flow rate, then you multiply by density, it becomes mass flow rate. Okay, so volumetric flow rate should be equal to, from looking at the unit, it should be equal to velocity times the cross-sectional area, right? Velocity is meter per second, the cross-section area is meter squares, and it becomes cubic meter per second for the volumetric flow rate. However, not all the cases like that. So a very big conditions you need to consider is whether the flow is uniform or non-uniform. Remember, we talked about uniform and non-uniform before, right? If it's uniform flow, sure, it's easy. Q equal to V times cross-sectional area, A, okay? Because the velocity is constant on that cross-section. It's easy to do. But if the flow is non-uniform, then what does non-uniform mean? Non-uniform means the velocity is not constant on that cross-section. So, okay, which velocity you pick? It's not constant, it's different everywhere, right? So, just like a pressure and a force, the plane force. If the pressure is constant on the plane, it's easy, pressure times the area. But if the pressure is not constant on an inclined surface, then you have to go through the integration. Same thing here. If the flow is non-uniform, velocity is not constant on the cross-section, the volumetric flow rate Q will be equals to integration of V dA, right? So if that's the case, it's non-uniform is the case, then the calculation will be a little difficult. We need to use integration. Okay. Then after you get the volumetric flow rate, convert to mass flow rate is easy. Just multiply by a density. In our class, in this fluid mechanics class, the density is constant always, right? Incompressible fluid. Okay, so this is the flow rate calculation. Okay, next let's do an example. Okay, here's the example. Let's say we have a pipe flow, okay, a circular pipe. Okay, so the pipe flow is non-uniform, obviously. Okay, I draw a flow distribution here. It looks like in the center it has high velocity and it has low velocity near the wall, and it's a parabolic shape of the velocity distribution. So we have to use, for this type of problem, we have to use cylindrical coordinate. Okay, cylindrical coordinate. I don't know if you still remember cylindrical coordinate. Okay, you have the flow direction, we said Z, or you want to say X. That's the flow direction, right? Stream Y direction. Then you have a radial direction, R, right? So in this problem, the velocity is the function of R only. Let's say it's fully developed. It has nothing to do with Z. It doesn't change with Z direction. Okay, it's a function of R only. So it changes when R changes. Okay, that makes sense? Okay, so what is the flow rate of this pipe? Okay, you are given an expression for velocity as a function of R. Okay. So the question you ask yourself, hey, is this flow uniform? Because here he said if it's uniform, then the flow rate is just velocity times area. If it's none, then you have to do integration. Obviously, this answer is no, it's not uniform, right? Okay, so we'll have to go through the difficult route. Okay, so the Q equals to, let's write down the equation first. The Q equals to VRdA, okay? So velocity is the function of R, so your dA has to be changed into right into something R, right? How do we construct the dA? That's the next step. Okay, so I have a drawing here. That's probably how do we need to construct the dAs. Okay, so this is R direction, so I draw a bend, a ring. Okay, that's your dA. That's your small element for the integration, right? So what is the area of this ring? Okay, it's the circumference of the ring times the thickness of the ring, right? dA equals 2 pi r, which is the circumference of that ring, times dr. dr is the thickness. Okay, be careful, this is calculus. Okay, now we know that. So the flow rate of this is V integration of VR times 2 pi r dr. So if you are given a actual expression for VR, you can integrate it out. Be careful the limits from 0 to the radius of the pipe, of the circle. Okay, if you are given those information, you should be able to calculate it. Okay, this is our example to calculate the volumetric flow rate. The mass flow rate is easy, just times the density. Okay, for uniform flow, it's really easy, just velocity, the constant velocity on the cross section times the area of the cross section. Okay, so this is our lecture about the flow rate calculations.